Okay, so in your first video, we talked about what is dynamic equilibrium. Essentially, we reach a point of equilibrium where the rate of reaction stays constant for the forward and reverse reaction, and the concentration stays constant of each of the products and the reactants. However, the reason why we say it's dynamic is because the forward and the reverse reactions are still occurring. It's just that they're occurring at the same rate, and so the concentration stays the same. Now, we can shift where that point of equilibrium lies. It might be that it favours the forward reaction, or it might be that conditions favour the reverse reaction. If we take this example here, we have nitrogen reacting with hydrogen to produce ammonia. We can see that the forward reaction is exothermic, so it gives out energy. The reverse reaction is endothermic, so it takes in energy. So how is this going to affect what can we do? How can we take advantage of this to affect its point of equilibrium? Well, an endothermic reaction, because it takes in heat energy, would need energy in order to take it in. So if I increase the temperature, it's going to favour the endothermic reaction. So we'll say it prefers hotter temperatures. Now the exothermic reaction doesn't need hotter temperatures as much because it can produce its own heat. Once it's got going, then any energy it would need to continue to go is producing it itself. So it doesn't need heat. The endothermic needs it more than the exothermic, so this would prefer cooler temperatures. However, there is still a trade-off, and you'll learn about more about this in the Haber process, because if we produce it, so let's just write this down. So it prefers cooler temperatures, or let's say less hot temperatures for now. Okay. The thing is, though, if we made it too cold, then the rate of reaction is going to be quite slow. So all reactions, whether they're exothermic or endothermic, are still going to be better in hotter temperatures because the reaction speeds up. Okay, it's just that a hotter temperature will speed up this one more than it will speed up that one. Okay, now what about pressure? If we look at these, if we look at this balanced equation, what it's saying is that one molecule of nitrogen would react with three molecules of hydrogen to produce two molecules of ammonia. So let's just draw that out. So on the left-hand side we have this, and on the right-hand side we have this. Now you will learn this in a different topic in chemistry that all molecules take up roughly the same amount of space when they're a gas. So a mole of nitrogen takes up the same volume as a mole of hydrogen. A mole of ammonia takes up the same volume again. And that's something you'll learn about in a different topic. And this would mean that this amount, basically, we're not so interested in what the molecules are, we just want to know how many molecules in total there are. And on the left-hand side, we have 4 molecules. And on the right-hand side, we have 2 molecules. So the left-hand side is going to take up twice as much space as the right-hand side, twice as much volume. It's going to need twice as much volume. So let's have a think about would these guys or these guys prefer a higher temperature? It's going to be these ones, because if we increase the pressure, therefore squash it, then these ones take up less space, and so it kind of encourages these to be formed, whereas these would need more space. So high pressure high pressure favors less molecules. So what would be a good trade-off to make it? If I wanted to have lots and lots of ammonia, I want to have a high pressure and I want to have relatively cool temperatures. But and you'll learn about, like I said, you'll learn about this from the Haber process a bit more. The trade-off, though, in both cases, in the terms of high pressure, is going to cost a lot of. It's going to use up a lot of energy to get things to go into a high enough pressure, and it could be quite dangerous. We don't want explosions, so there's a trade-off there. We can make it, you know, high enough that within such that it's not too dangerous and it doesn't cost too much money or use too much energy. And we want it relatively cool, but not so cool that we have to wait around for ages for the reaction to happen. So but apart from those trade-offs, we want ideally high pressure and relatively low temperatures. Okay.